Okay, good afternoon. My name is Louter, Professor of Structural Design and Building Engineering at TU Delft. And I'm happy to be here together with my colleague Pfarr, who is a researcher at the Institute of Building Construction at TU Dresden. And today we want to show you our research about thin glass composites with a 3D printed core pattern. This is just a small example or a small sample of it. The idea is that we combine very strong thin glass to make a very lightweight and strong composite panel that we intend to use as a facade or perhaps as a roof, or even you could think about a floor system. And the benefit is that you use much less material than conventional glass, as you see here in the building today, and that you can also optimize or customize your pattern that you see in between the glass. Just as a short outline, we present a little bit about the concept of it, the upscaling, the performance, a short outlook into what will be the next step, and then we close it up. So first of all, the concept. So how did we come to this idea? It started all with thinking about how you can use thin glass, and then I refer to the glass that you have on your devices, your mobile phone or your tablet, which is in the range of 0.1 to 2 millimeters, let's say. And it's very strong because it has been chemically strengthened, so 10 times stronger than regular glass, more or less. And it's also very flexible, so you can easily flex the glass in desired curvatures. So this is a piece of thin glass, and you can see that you can easily bend it into desired curvatures, so by hand, by cold bending, we call that. Many people think it's plastic, but it's really glass, actually. Here you can see a small test on 2 millimeter glass, so actually in the thicker range, I would say. So we do some column buckling by pressing it downwards, and you can see the glass quite bending outwards. We have a strain gauge on there to measure the strain and calculate the stress from that, to see how far we can bend it before it fractures. And then it slows down the video, because we arrive at the full fracture. Just one disclaimer, it explodes quite explosively, because there's a lot of strain energy in the glass. If I would drop this piece of glass, it will fracture in big pieces, so a bit safer than this. But now we have so much build-up energy that once it breaks, it's exploding in all directions. So very strong thin glass. Here you can see a plot of it. We reach strength values of well over 400 megapascals, and actually in this setup it failed from the clamp, so we could push it much further, but we had to improve the setup for that, and then you can get to 800 or 900 megapascals, which is let's say in the range of high strength steels. So we had a series of master students looking into what can you do with it. So first concept was to look into adaptive facades. So on the right-hand side, you see a shape memory alloy activated thin glass facade that opens up. So by pulling up this bar in the middle, you will open up your facade for ventilation when it's too hot, and then when it has cooled down, then it closes automatically again. And this makes use of the flexibility of the thin glass. But then other concept that we would like to talk about today is more to combine the thin glass with a core pattern to stiffen the glass, because you can imagine that this vibration is too much for a building. It's causing noises, it's causing too much deformation and too much nuisance for building occupants. So we thought about combining it with more conventional, on the left-hand side, closed cell or honeycomb kind of patterns, but also perhaps with open cell configurations. And there the idea came also to print those patterns. And the first student looked into that to print a truss structure. That's what you see here, so that you have a pattern that is stiffening the thin glass for that, and that you create this very lightweight thin glass facade panel. Of course, we tested that in a very small scale, really A4 scale, and luckily also it worked with our analytical model, so it combined very well. And then we had next steps in a student looking into can you use Voronoi optimization there or tessellation there to create perhaps a bit more structurally optimized pattern. And at the same time, you can imagine that you have now viewing zones in your glass that you can look through, and you also have zones which are blocking the sun and provide a bit of shading there. So he made quite some nice samples there. Some of these are also passing around in the audience. And he also proposed a nice design of how to implement that in a building or a roof or a facade. And then optimizing your core pattern for structural, but also for daylighting purposes, that you can really regulate how much light you can get into your building. And the next step was to look into, okay, since the glass is easily bendable, can we also exploit that to make curved 3D printed patterns and then glue the glass easily on top of that. And you don't need any heat or something to bend the glass, so you can easily bend it, let's say, by hand and make these small scale curved composite panels. Then for a while I moved to TU Dresden for 3 years as a professor of building construction, where I met Daniel first as a master's student and later as a researcher PhD student. And one of the focus there was to really upscale this concept. So we looked into how can we make it bigger. And the first idea was to stitch smaller prints together, which of course worked well, but it was still quite labor intensive. And Daniel devised a very nice interlocking scheme that you can stitch such smaller panels together. At the same time, of course, it's not shifting. Yeah. At the same time, of course, there was the challenge of gluing. So we are gluing the thin glass to the pattern, which was done manually at that time. And of course, there we also wanted to see if we can automate that process and be more efficient there. So the whole question was about how do we get from a small scale A4 sized panel to a big scale panel. And we saw no other option than to apply for a significant grant or significant fund to buy a large robotic 3D printer. And luckily we got the grant. So here you see a 4 by 2 meter print bed, which can be heated, and the robotic extruder there, or the robotic operated extruder there, to be able to print our facade scale kind of patterns. So how do we do it? So we can print different kinds of polymers, either with or without glass fiber reinforcement in there, or opaque or also a bit more translucent. And we prefer to print on a flat piece. So here we're printing on aluminum, which is heated then from the bottom by the heated bed. But later you also see that we print on glass directly to have a very smooth surface to be able to glue to. And then in the next step, we grind the top surface. So the top surface is milled off, also robotically, just to be able to get a perfectly smooth surface again to be able to glue on it. And that gluing is then done in the next step by this also robotically operated reservoir, let's say, applying the glue with specific pressure and specific speed. And this glue is UV curing, so it's only getting rigid, let's say, if you apply UV light from the sun or from an artificial light. So until that point that you apply the light, you can still maneuver and you can still take your time to apply the adhesive, let's say. Another thing is that this adhesive is very thin normally, less than 1 millimeter, so you don't have that much tolerances to compensate, or not that much capacity to compensate for tolerances. That's why we really want to mill it down to have a smooth surface for the gluing. And later you will see also Daniel will show a bit more about hot melt adhesive, which are a bit more tolerant in terms of sizing. And then we come to the assembly. So here you see the robot still applying the glue, and on the right hand side you see the thin glass being laid down by suction cups already, ready to be moved on top of the adhesive there. Now it's there, and then the next step would be to illuminate the adhesive with UV light. So following these 4 steps of additive manufacturing of the core, then to mill down the core to facilitate adhesive bonding, and then adhesive bonding and the assembly. That's our process to come to really large scale or full scale facade prototypes that we can then also test in the lab. And there comes in the research of Daniel, who is looking into the design and the performance of such panels.
Yes, thank you very much for having me here as well. Yeah, when it comes to performance, we can of course talk about different objectives or different categories. Today I want to give a brief introduction into some mechanical properties at first. And because we want to achieve a facade element, so the idea is very close to test it in a wind load test. Therefore, we have a big facade testing wall at our laboratory in Dresden. You can see here already in the to the right-hand side the test specimen, which is built into the facade test wall. On the left picture, that's the technical drawing. That was already only a preliminary test at first. Dimensions from roundabout almost 2 meter by 1 meter in size. And you can see the honeycomb structure, which is 14 millimeter thick. It was a PETG based polymer with 20% glass fiber. And on the top, on each side, we glued a still 3 millimeter thick, I would say, glass sheet on it. And yes, the whole test specimen was supported on each side, and we can blow in and suck out air into the cavity behind the facade element. And yeah, we test the element until 4000 Pascal, which is still quite a lot. So if you would want to calculate the facade panel, you would estimate in Germany, as far as I know, 1500 Pascals. So it is a really strong wind load on this panel. And we tried to measure everything with the DIC system, with the digital image correlation system, so that we get some deformation and displacements from the panel when it is loaded. And when we look into evaluation, we compared two different systems. So in the top or in the bottom part of the picture, you see the DIC picture. So that is the actual deformation of the panel during the loading. And on the top, there's a finite element simulation, which represents the physical tests quite well. And we measured at the maximum load of 4000 pascals, only 2.3 millimeters deformation. And just to compare it a little bit to other structures or glass structures, that would be the same or roughly the same deformation which you would get when you have a 12 millimeter monolithic glass pane, so one solid glass pane. And that already means that we save 50% of the glass used, and we only have 40% less weight, because we are adding a little bit of weight during the additive manufacturing process. Another example to compare it with is an IGU, so an insulating glass unit that is probably more common, like you see here in the facade as well. There you have a 10 millimeter glass sheet outside, a 16 millimeter cavity filled with air or the different gas, and an 8 millimeter glass sheet in the inner side, and that would mean already 70% less glass and 65% less weight. And in our current project, we are investigating, okay, what impact can we expect to CO2 emissions or other environmental aspects, and therefore we have a test facade or an example, which is a building in Dresden that is kind of a conference center, or our students have their lectures there. And only this facade, what you can see here in the picture, is 300 square meters of glass, which means already 30 tons of glass. And only the production of this glass would make 20 tons of CO2 equivalents. And so our idea is basically to not only reduce the mass in the building, but also reducing the material from this energy-intensive glass. And so switching from the left side, from the traditional IGU, to a right side, to a composite panel with only 2 millimeters glass on each side. And there we can expect a lot of reduction in weight and CO2 emissions.
Yeah, so far we have mostly looked at the structural performance of the panels, but also thermal performance is an issue, of course, that we need to have a closer look into. On these images, you can see some models of the thermal model, let's say, and you can see that we are losing heat at some points. and that's where you expect where the core is touching the glass, let's say. So there we see some thermal bridging happening, of course, because normally an IGU or insulating glass panel doesn't have this core inside. But now with the blue core that I drafted there, you see that there's a thermal bridge coming from the left to the right-hand side of the glass, so bringing your heat or your cold to the other side of the panel, which we would like to prevent, of course. I cannot point with this computer, but the idea is then to perhaps to apply a second layer, as you also see now with triple IGU, triple insulating glass, and make sure that the cores in these two individual chambers doesn't touch, or they don't touch, so that you don't have direct conduction there. Or simply apply an extra layer with a cavity which is empty, which can still benefit actually from the stiffness of the other panel. But in this case, you avoid this thermal bridge from inside to outside. And the other option is to separate the core, let's say, to make two cores, to print them on either side of the glass panel, so that you avoid that this core is bridging from the one to the other glass. And another issue that we would like to look into a bit more later is also daylight control. Of course, this panel can be optimized for structural purposes, but also for daylight control purposes. So having more pattern where you would like to block the light, incoming light, and having a more open pattern when you would like to have the view or the light in. And perhaps also to use the curvature or the angle of the pattern to reflect light inwards or to the ceiling as you wish. So here you can see some render on the left-hand side, but also you can see that the shading already indicates a little bit of what you can achieve in this respect.
Yes, then let's come back a little bit to 3D printing again. What we are looking right now is actually to go to curved panels. We have the robotic arm, we have the thin glass, which is very flexible, so we want to make use of it. We have the potential of computational design to design in a variety of geometries. And so the next idea is to go for curved panels, and therefore we need design procedures, production procedures, which can be automatic, which can be automatically. And so here on the left side you can see rendering how we could design a panel like that. So we are directly designing the print path, which is expected later on with the robot. And then we are projecting it to some kind of free form which represents the facade. And on the right hand you can directly see it doesn't matter which panel you are choosing, the print path is directly generated, and we can transport it or we can give it to the robot and it will additive manufacture the core structure. And there's also included that the gluing after the printing or the milling process if needed. And so we want to have a file to factory process which is almost digital until you come to the real printing. How we start with that is that we just milled out this kind of formwork. So that's the wooden formwork, which is as well parametric designed, so we can easily change it, and it is quite low cost to produce it. So that is, for example, the milling process, which is needed then to get the shapes, and then we just simply put the wooden blades together once we have changed the shape of them. Yes, and then we have a curved surface which we can print on. You can here see a very thin sheet of glass, so this is only 0.7 millimeters thick. We can heat it from below, and then we can directly print on the curved surface. And we have a curved core structure. And the next step is to glue it somehow, and therefore we already heard about the acrylic, which is UV hardening, but it's very like honey, so when you have a curved surface it will flow down to a certain point. So we are investigating new methods to glue it. One promising example could be the hot melt, which we are using here. So we just mounted a hot melt glue gun on the left side to our robot, and then we took the same way like the last layer of printing, and so we applying the hot melt. That is totally fine when it's cooled down, because then we go to a second lamination process where we stack up the glass with the core structure, and then we put it into the oven, and then we are laminating the core and the print together. Yes, and some closing words then again.
Yeah, so we come to the end of the presentation. Still a lot of work to do in the next years, I think. But we would like to convey the message that we're working on strong and stiff, yet very lightweight facade panels, or floor panels, or roof panels, which have less embodied energy than conventional facades. And you can also optimize the pattern according to your performances, or also do your architectural intent, let's say. This presentation is short. You can read more in the BEAM booklet, or in the meantime you can also look at one of our recent journal papers published with Springer in the Architecture, Structure and Construction Material journal. Sorry. And we would like to thank very much the funds that we have obtained for the printer itself on the left-hand side, but also for continuing in a project with several partners at TU Dresden that is looking more into the real implementation of such components in facades. And we would like to thank you very much for your attention.
Yeah, fantastic. Thank you very much for the wonderful presentation and the projects. Do we have any questions from the audience?
Thank you for the presentation. I have a question. Am I understand right that the usage of glass with ultraviolet protection is not possible because of gluing process?
Yeah, you mean that if you have any UV blocking mechanism, that it would be difficult to use the UV curing glue. I think to a certain extent that's valid, especially if you come to a laminated glass. But the hot melt that Daniel showed in the end doesn't have this UV activation need. So that's heated, or that's cured by heat in the end.
Okay. And so for the second possibility for adhesive assembly, so it means last layer is not hot all the time. So glass will be put on top, and then it will be made. So you bring heat again.
Yes, so first we 3D print the core structure, then we take off the 3D printed core, and then we can put it back to apply the adhesive. Then we flip it around to put the adhesive on the other side of the core element, and then we have a core structure with two-sided hot melt, which is cooled down. Then we can stack the glass on it. We put it in a vacuum bag because we want to achieve the curvature as well, so it is pressed down to the adhesive, and then it comes to an oven at 120 degrees, for example. And then the hot melt is melting, and it's reconnecting, and then it's connecting the core structure with the glass. So it's a second step after the printing.
Thank you.
Welcome.
Thank you very much. Do we have any further questions? Sorry.
Thanks for the presentation. I have a question if you have looked into the full life cycle, because I guess you can't get around this topic these days anymore, and if you have looked into this, how to recycle or what to do with the product once it's not needed anymore, because the glass only, I guess you could recycle, and then there's plastic glued onto it.
Yes, a very good question. That is a big part of our current research project, which is now running for 1 year, and so we still have 2 years left. So at first we looked into the A module of the building cycle, so only the production of the materials and the CO2 emissions during production. The next one will be the living phase. So now we have to care about U values and performance in terms of thermal insulation and things like that. And we go the full circle until the D level. and we want to, or we make concepts how to recycle it. The UV hardening acrylic is very challenging to recycle because that is like, yeah, the bond is very strong and we can't really disassemble the whole product. The hot melt is a little bit more beneficial because we can just heat it up to 90 or 100 degrees and then we can take it off, so that's the idea. But yes, we're still working on concepts how to completely disassemble the whole product, but that's a little bit way to go still.